Comprehensive study on microstructure and strength of graphite-molybdenum brazed joints. This important article is authored by the following scientists. Production of permanent joints of high-temperature materials, molybdenum and graphite, by brazing is very important for many branches of industry related to structural operation at high temperatures. By selecting a brazing filler metal for joining dissimilar materials, several critical factors must be considered, including chemical composition, melting point, thermal expansion coefficients, mutual diffusion processes, wetting behavior of the base material, and residual stresses. This chapter provides a concise overview of brazing dissimilar carbon materials with molybdenum, presenting the microstructural characteristics of brazed joints and evaluating their mechanical properties using different alloying systems in the brazing filler metal. Due to diffusion processes, carbide compounds form at the brazing filler metal carbon interphase boundary. These compounds may appear as a continuous layer along the brazed seam or as discrete islands within the seam and porous graphite. The latter configuration is preferable for enhanced mechanical performance. Graphite-molybdenum brazed joints hold significant potential for applications in the aerospace, nuclear, automotive, and medical industries. They are particularly valuable in the production of critical components for thermonuclear reactors due to their excellent high-temperature properties. Introduction. In industries like aerospace, nuclear energy, and electronics, engineers often need to join different materials together to make high-performance parts. One powerful technique for doing this is brazing, which uses a melted metal, called filler metal, to bond materials without melting the materials themselves. However, when working with very different materials, like graphite and molybdenum, brazing becomes more complicated due to their unique properties. Graphite is light, handles heat well, and doesn't expand or crack easily. It's used in high-temperature applications. Molybdenum is a tough metal that also handles high temperatures but is sensitive to oxidation. It reacts badly with oxygen at high heat, and changes shape under extreme heat. Joining these two materials is tricky. They don't naturally stick together well, and the filler metals commonly used, like silver or copper-based ones, don't bond strongly or withstand high temperatures. Special filler metals called adhesion-active fillers are used instead. These include elements like titanium, zirconium, chromium, or vanadium, which chemically bond with graphite by forming carbides, hard compounds that improve the joint's strength. The key to success is using the right filler metal mix and controlling the brazing temperature. Too much of the active elements can make the bond brittle. Too high a temperature can damage molybdenum by changing its structure. By experimenting with new filler metal combinations and improving the joining process, such as applying pressure or pretreating the surfaces, researchers have improved the strength of these joints. For example, some filler metals achieve joint strength up to 28 MPa, a measure of how much force the joint can handle, which is a big improvement. New techniques also reduce cracks and ensure smoother bonding between the materials. In summary, this research focuses on developing better, stronger, and more heat-resistant methods for joining graphite and molybdenum, which helps create more reliable components for high-tech industries. Conclusion. Scientists are working on better ways to join two very different materials, graphite and molybdenum, which are both used in high-temperature industries like aerospace and nuclear energy. The challenge is that these materials don't naturally stick together well, especially under extreme heat. To solve this, a process called brazing is used, where a special metal alloy, called filler metal, is melted to bond them without melting the materials themselves. Recent tests using micro-X-ray analysis show that during brazing, the molten filler metal actively reacts with graphite and molybdenum, forming strong chemical compounds known as carbides. These carbides form at the joint seam and strengthen the bond. The type of carbides depends on the filler metal used. For example, titanium-based fillers form titanium carbides, while others with zirconium or palladium form their respective carbides. Newly tested filler metals, especially those based on PDNiCrGe and ZrPD systems, have shown excellent results. These metals not only form a strong bond but also stay stable during the brazing process. In strength tests, these joints withstood up to 36 MPa, which is very promising. Interestingly, when the joint breaks, it's the graphite that gives way, not the joint itself, showing how strong the brazed connection is. As new high-performance graphite and carbon materials are being developed, it becomes more important to create reliable, heat-resistant joining methods. These findings help move us closer to creating stronger, more reliable parts for the next generation of advanced technology. Thank you for watching this video. Please subscribe to our channel BP International to watch more videos in the fields of science, technology and medicine.